In this podcast, we're going to give you an introduction to oxidation reactions. We're going to go back to our previous intro to chemistry class and talk about redox reactions, and then talk about how they're different in organic molecules. And we'll show you how to do an oxidation reaction for a primary, secondary, and tertiary alcohol. All right, so I'm sure it felt like a lifetime ago that you had to write redox reactions back in intro to chemistry, and you had to write those half reactions, and we were really concerned with what was happening to the electrons. Are we losing electrons? Are we gaining electrons? And that was how we defined our redox reactions. So in your notes, you would write down that an oxidation is the loss of electrons. What you also wrote down, and we didn't really pay attention to because it didn't work out for us with ionic compounds, was that it's also a gain of oxygen. We also talked about reduction reactions, which are a gain of electrons. And again, you wrote this down, but we didn't pay much attention to it and we didn't get to use it. Reduction is a loss of oxygen. So we're not going to worry so much in organic about following those electrons as we are looking at, are we increasing the number of carbon-oxygen bonds? Are we oxidizing, or are we losing carbon-oxygen bonds, hence a loss of oxygen? All right, so when we think about oxidation in organic molecules, I want you to think about oxidation as being a result in an increase in the number of carbon-oxygen bonds. So we're increasing carbon-oxygen bonds. And in order to increase that, we're going to have to, at the same time, decrease the number of carbon-hydrogen bonds. So if I want to do a shorthand in my notes just to kind of jog my memory, we're increasing carbon-oxygen bonds and we're decreasing carbon-hydrogen bonds. So that's my cheat sheet for oxidation. Later on, we're going to talk about reduction, which is the opposite process. But for now, let's just focus on oxidation. In an oxidation reaction, and I've written this O over the arrow, that means that we have an oxidizing agent of some sort. We start with an alcohol, and we are going to decrease the number of carbon-hydrogen bonds. So we lose a bond here. And in order to increase carbon-oxygen bonds, we're going to have to get rid of this hydrogen so that we can add in a second or a double bond between carbon and oxygen. So notice that we've lost two hydrogens. When you lose those two hydrogens, 2, 3, 4, okay, so we have an opening here and here. Those valence electrons are going to come into this double bond and be shared between both the carbons and oxygen so that they can maintain their octet. So we will start with an alcohol and we will end with a carbonyl when we oxidize. All right, let's get a little more specific and talk about a primary alcohol. And remember, a primary alcohol, the alcohol carbon, so this guy is attached to one or no other alkyl groups. So when you have a primary alcohol, you have two different carbon-hydrogen bonds, and that's going to be critical to understanding how many steps this oxidation is going to have. So we will start with our primary alcohol. After the first oxidation, we will get an aldehyde. And after our second oxidation, we will get a carboxylic acid. All right, so you're going to have an oxidizing agent for this. We could use potassium permanganate, or I just like to use the O over the arrow. We won't talk about specific oxidizing agents. All right, so remember from the last slide, what we're going to do is we are going to decrease our carbon-hydrogen bonds. We're going to lose a carbon-hydrogen bond, and we're going to lose the hydrogen that's attached to our oxygen. What this is going to do is it's going to provide a double bond, or we formed a carbonyl. Something to keep in mind is that we still have this carbon-hydrogen bond right here. So we have one carbon-hydrogen bond, your R group is still there, but now we have the presence of a carbonyl. It's at the end of a chain, so we consider this an aldehyde. In our second oxidation, and the reason it has another oxidation is because we still have a carbon-hydrogen bond. So we can actually remove this last carbon-hydrogen bond and we can replace that with an OH. So we wind up with our functional group is a carboxylic acid. At this point, there is no further oxidation because our carbon has no more hydrogen bonds on it. All right, so we talked about oxidation primary alcohols. In a primary alcohol, we have at least 2 carbon-hydrogen bonds. Now in a secondary alcohol, we have only 1 carbon-hydrogen bond because we have 2 R groups attached to our alcohol carbon. So in this situation, we can only have a one-step oxidation reaction because we only have 1 carbon-hydrogen bond to decrease, resulting in an increase of 1 carbon-oxygen bond. So this is going to work the same as it did before. We're going to lose our carbon-oxygen bond. We're also going to lose the hydrogen off of this oxygen. What that does is provide us a space to form a double bond with the carbonyl. This time your difference is you're starting with a secondary alcohol, and because you have 2 R groups that aren't going to change, and your carbonyl is going to wind up in the middle of those 2 R groups, you're actually winding up with a ketone at this point. So again, oxidation is an increase in oxygen, or an increase in carbon-oxygen bonds, and a decrease in carbon-hydrogen bonds. This cannot undergo further oxidation because I don't have any carbon-hydrogen bonds to decrease anymore. So this is where our oxidation would stop. Oxidation of tertiary alcohols are the easiest oxidation reactions to do. Let me tell you why. On our alcohol carbon, so this guy right here, there are no carbon-hydrogen bonds, none at all. Because there's no carbon-hydrogen bonds, I can't decrease the number of carbon-hydrogen bonds, so therefore it won't go through an oxidation reaction. So this would be a no reaction because there's no hydrogens available on the alcohol carbon. This is the one that we always hope will show up on a quiz.